Welcome to the deep dive. You know, we don't just skim the surface here. We dig into that really dense foundational stuff. The physics that actually makes things work.
Yeah, the core principles.
Exactly. And today we're doing a fundamental deep dive into dynamics. We're talking Newton's laws of motion, what mass really is, and the surprisingly tricky concepts of friction and freefall.
It's the shortcut, really, to understanding how things move, from,
Yeah.
throwing a ball to launching a rocket.
If you want that core understanding, you're definitely in the right place.
And the material we've been looking at for this, it's really quite thorough, comprehensive instructional stuff on mechanics.
Very structured.
Very. It forces you to confront those common mix-ups, like the whole mass versus weight thing. We'll definitely get into that.
Absolutely. So the mission today, simple. Pull out the key equations, the ones that matter, find those surprising real-world examples, and, bust some myths.
Get ready for a few aha moments, hopefully.
Should change how you see forces all around you. Okay, let's kick off with friction. That force that decides if you can, say, push a heavy box or just slip, it's always opposing motion.
Right, the universal opponent. And this is where it gets really interesting, because microscopically, it's not just about things being rough.
Not just sandpaper on wood.
Not fundamentally, no.
Yeah.
Even surfaces that look incredibly smooth, polished, under a microscope, they have these tiny peaks and valleys.
Okay.
And when you press two surfaces together, even lightly, these little irregularities get so close that the atoms, well, the electromagnetic forces between them, they kind of weld together on a tiny scale.
Atomic welding. Seriously.
Sort of, yeah. Cold welding. So friction, at its heart, is the force you need to apply to break those microscopic bonds just to get things moving or keep them moving.
If it's atomic welding, how do lubricants work then? Like oil?
Yeah.
Seems like that should make it stickier.
Good question. The lubricant basically gets in between the surfaces. It creates a thin film.
It separates them.
Exactly. It separates them just enough to reduce that close atomic interaction. Less chance for those welds to form. It acts like a shearable layer.
I see. That makes sense now. And we need to talk about the two main types of friction, right? Based on whether something's moving or not.
Precisely. First up is static friction. This is the force that holds something still. Think about trying to shove a really heavy filing cabinet.
Yeah, you push, nothing happens.
Right. You push harder, still nothing. That's static friction matching your push, resisting, but it has a maximum value.
A limit.
A limit. Once your push exceeds that maximum static friction, then it starts to move.
Okay, so static friction prevents the start of motion, but once it is moving.
Then kinetic friction takes over. This is the friction that opposes motion while the object is actually sliding or rolling.
And kinetic is usually weaker, isn't it?
Almost always, yes. That initial push to overcome static friction, that's typically the hardest part. Once it's sliding, it often feels a bit easier.
And both types, static and kinetic, they depend on how hard the surfaces are pushed together.
Correct. They're proportional to what we call the normal force. Basically, the perpendicular force squeezing the surfaces. More squeeze, more friction, generally speaking.
Let's make this real world. The sources mentioned tires and ABS braking systems. How does friction play in there? Is tread just for water?
Great example. No, tread is crucial for more than just water. It allows the rubber components of the tire to deform and interact properly with the road surface. Now, ABS, anti-lock braking, that's clever physics.
How so?
ABS doesn't get rid of friction. It works by rapidly pulsing the brakes on and off
Why?
to stop the wheels from locking up completely.
Why is locking up bad? Isn't skidding maximum braking?
No, actually. Remember, static friction is usually stronger than kinetic friction.
Right, the initial hold is stronger than the slide.
Exactly. When your wheels are rolling without slipping, they're using static friction to grip the road. That's your maximum stopping force and steering control. If the wheels lock up, you start skidding.
And switch to the weaker kinetic friction.
Precisely. You lose steering, and braking is less effective. ABS tries to keep the tire right on the edge of slipping, constantly trying to maximize that static friction grip. It's about controlling the flip to maintain the best possible stop.
Wow. Okay, physics mastery in action, like you said. So we've covered resistance from contact friction. Let's switch gears to resistance that's built into matter itself. Inertia, mass.
Which brings us, yes, to maybe the biggest confusion in everyday physics talk.
Mass and weight. We use them like they're the same thing all the time. I need to lose weight.
Yeah.
But in physics, totally different. Let's unpack that.
Okay, mass. Think of mass as the fundamental measure of inertia. It's how much an object resists changes in its motion, how much stuff is in it.
Right. Resistance to acceleration.
Exactly. And crucially, mass is intrinsic. It's constant. Your mass is the same whether you're on Earth, the moon, Jupiter, anywhere.
Yeah.
If you have 80 kilograms of mass, you always have 80 kilograms of mass.
Okay, mass is constant stuff, but weight, that's where it gets confusing, right?
Yeah.
Because weight can change.
Weight is a force. Specifically, it's the force of gravity pulling on that mass. The equation is simple. $1 equals mass times g.
Where m is that constant mass, and g is the local acceleration due to gravity, which changes depending on where you are.
Ah, so that's why weight changes. If mass is constant but g isn't.
Then weight isn't constant either. Take that person with 80 kilograms of mass, same mass on Earth and the moon. But the moon's gravity, its g, is only about 1/6 of Earth's.
So their weight on the moon is way less, about 1/6.
Exactly. That's why astronauts can bounce around and lift heavy things easily up there. It's not because the objects have less stuff in them.
They still have the same mass, the same inertia.
Right. It's just that the force pulling them down their weight is much weaker because the moon's gravity is weaker. Resistance to moving them is the same, but the force you're fighting against gravity is less.
That's a really crucial distinction. So weight loss technically means mass loss, but weightlessness in space means lack of gravitational force, or near zero g. You've got it. And the units help keep this straight too. Mass is in kilograms, kiloj weight. Weight, because it's a force.
It's measured in newtons.
In, yes. And a newton itself is defined based on mass and acceleration. It's the force needed to make 1 kilogram accelerate at 1 meter per second squared. So 1 n equals 1 kilojoule ms fucking heves. The units embed the concepts.
Okay, we've got mass as inertia, weight is the force of gravity. Now let's connect force and motion with the big one, Newton's second law. All right, moving beyond just defining things, Newton's second law. This is the core formula, isn't it? It links force, mass, and acceleration. F text net.
That's the one. Net force equals mass times acceleration. Or, rearranging it, acceleration equals net force divided by mass. F aces F text net.
And understanding the relationships here is key, the proportionality.
Absolutely fundamental. Two key things jump out from F text net for. First, acceleration is directly proportional to the net force.
I mean,
Double the net force on an object, you double its acceleration. Push it twice as hard, its speed changes twice as fast. Simple cause and effect.
makes sense. More force, more acceleration. But the relationship with mass is different.
It's inversely proportional. That reflects the inertia we just talked about.
So double the mass.
You have the acceleration, assuming the force stays the same.
Yeah.
Think about pushing, say, an empty shopping cart versus a full one with the same effort.
The empty one takes off way faster.
Exactly. Same force, much less mass, much more acceleration. The full cart has more mass, more inertia, so it accelerates less for the same push. That difference is purely down to mass resisting the change in motion.
Okay, I get the overall idea. $5 is fuss. But forces in the real world aren't always neat and tidy, pushing straight ahead. What about forces at angles? How do we find that, the net force?
Good point. That's where vectors come in. Force is a vector. It has magnitude and direction.
Right.
To find the net force, you have to add up all the forces acting on the object, considering their directions. Gravity pulling down, maybe friction opposing motion, maybe you pulling at an angle.
Like pulling a kid on a sled with a rope that's angled upwards.
Perfect example. That pulling force isn't purely horizontal. It has an upward component and a forward component. To use $y mole properly, you have to break that angled force down.
Split it.
Yeah, into perpendicular components, usually a horizontal part and a vertical part. By Othrail, you resolve the vector.
And then you can analyze the horizontal motion using only the horizontal forces and the vertical motion using only the vertical forces.
Precisely. It simplifies the problem immensely. You calculate the net horizontal force to find horizontal acceleration and the net vertical force for vertical acceleration. That's how you handle complex situations and find the true FedNet doll.
Okay, let's apply these ideas to falling objects. We usually start with Galileo, right?
Right.
The idea that in a vacuum with no air resistance.
Everything falls at the same rate, regardless of mass.
Yeah, a feather and a hammer dropped on the moon hit the ground at the same time. They accelerate constantly at g. On Earth, that's about 9.8 meters in Trek.
That's the idealized physics picture, but here on Earth we have air.
Which means air resistance.
Yeah.
Drag.
Exactly. Air resistance, let's call it $2, is a force that opposes motion through the air. So for a falling object, the net force isn't just its weight, pulling it down.
It's weight down minus drag up.
Correct. Hick-Contain R2R. And here's the crucial part. Air resistance isn't constant.
It depends on speed, right? The faster you go, the more drag.
Yes, drag typically increases with speed.
No.
Sometimes with the square of speed, it gets complicated, but the faster you fall, the bigger do gets.
So if this $2 gets bigger as speed increases, the net force gets smaller.
Precisely. The object starts accelerating at g when torr is 0 initially, but as speed picks up, torr increases, free text net decreases, so the acceleration slows down.
It doesn't keep accelerating at 9.8 meter seconds forever.
Not in air, no. And this leads directly to...
Terminal velocity.
Yeah.
The speed limit for falling objects.
Exactly. What happens when the object falls fast enough that the upward drag force, $2, grows to become exactly equal in magnitude to the downward force of weight?
If torr equals then $2, then $2 0.
Right. The net force becomes 0.
And if F text net, then according to Fesmet Moore, the acceleration A must also be 0.
Bingo. The object stops accelerating. It doesn't stop falling, but it stops speeding up. It continues to fall at that constant maximum speed. That's terminal velocity.
The skydiver example is perfect here. Our sources mentioned a typical terminal velocity for a skydiver before opening the chute is around 180 kilometers per hour.
Yeah, about that. That speed is determined by their weight and their, aerodynamic shape, their surface area facing the direction of motion.
Okay, so they hit 180 kilometers is 0 constant speed, then they pull the ripcord.
And suddenly, bam, the parachute deploys. What does that do?
Massively increases the surface area.
Which massively increases the air resistance, $3. All of a sudden, $3 is much bigger than their weight. Bam.
So the net force in milligram is now negative, meaning upward.
Yes, a large upward net force, which means a large upward acceleration, or rather a rapid deceleration. They slow down very quickly until their speed drops enough that the new large drag force, $3 from the parachute, once again becomes equal to their weight, $1.
They reach a new, much slower terminal velocity.
Exactly. Slow enough for a safe landing. It's all about manipulating that drag force $3 by changing the surface area.
Yeah, okay, we've done forces on single objects, falling objects. Now, interactions between objects, Newton's third law.
The action-reaction law.
For every action, there's an equal and opposite reaction. Sounds simple enough.
It sounds simple, but it trips people up constantly. The absolute key insight, the thing you must remember, is that the action force and the reaction force always act on different objects.
Always on different objects. Why is that so important?
Because if they acted on the same object, they would simply cancel each other out, right? Equal and opposite forces on one object means 0 net force.
And nothing would ever accelerate. Nothing would move.
Exactly. The reason things move is that the action and reaction forces apply to different things, causing potentially different accelerations based on their masses.
Okay, give us that classic example. Walking. How can I walk forward if the ground pushes back on me with the same force I push on it?
Because the forces are on different systems. When you take a step, your foot pushes backward on the earth. That's the action.
Okay, I push the earth backward.
Simultaneously, the earth, thanks to friction, pushes forward on your foot. That's the reaction.
The forward pushes on me.
Yes. That forward reaction force from the earth is what accelerates you forward. The backward action force is acting on the earth, which barely notices because its mass is enormous.
So if I were on, say, frictionless ice,
you'd push the ice backward, action, but the ice couldn't exert much forward friction force back on you, reaction. So you wouldn't go anywhere. You need that reaction force.
that clarifies it perfectly. The forces are paired, but act on the two interacting objects separately. This explains rockets too, right?
Absolutely, textbook example. The rocket engine forcefully expels hot gas downward. That's the action.
Gas pushed down.
The reaction. The gas pushes the rocket upward, equal and opposite force. That upward push on the rocket is the thrust.
Lifts the whole thing. Amazing.
It even works on a cosmic scale. The Earth pulls on the moon with gravity, action.
And the moon pulls on the Earth with the exact same gravitational force, reaction. Equal and opposite.
Yep. The forces are identical. The reason the moon orbits the Earth, and the Earth wobbles slightly, is due to their different masses determining their acceleration from that mutual force, according to Thusmet.
It all ties back together. Third law sets up the interaction. Second law dictates the outcome for each object. Hashtag tag outro.
Wow.
Yeah.
Okay, we have covered a lot of ground today.
Uh,
A huge conceptual journey. We went from tiny atomic welds causing friction.
to understanding why mass isn't weight.
Used $5 to predict motion. Saw how forces need breaking down into components.
And ended up seeing how even falling objects reach a balance point at terminal velocity.
Having this structured understanding, it really is the key to getting dynamics, isn't it? It is. And seeing how Newton's laws aren't just separate rules, but a completely interconnected system, that's the real power. They explain everything from static friction holding a book on a table.
To the complex dance of forces letting a skydiver land safely.
It all comes down to force, mass, acceleration, and those action-reaction pairs. Governs everything we see moving or staying still.
Okay, let's leave our listeners with something to chew on. A final provocative thought.
All right.
We talked about air resistance and terminal velocity. Now think about this. Contrast a high-speed jet flying at a constant 1,000 kilometers per hour at a constant altitude. Its net force is zero, right? Constant velocity.
Right. Thrust equals drag, lift equals weight, balanced forces.
Okay, contrast that with a diver accelerating underwater. Water is way denser than air. How does the nature of that fluid resistance water drag versus air drag change the whole calculation? Think about how quickly terminal velocity might be reached, or how much force is needed to maintain a constant speed underwater compared to in air.
Yeah. How does that much denser fluid affect the balance of forces and the resulting motion? Something to definitely mull over.
Absolutely. That's all for this deep dive. Thanks for joining us.